You ever stop and think about what actually happens when you hit play on a YouTube video? I mean, it seems so simple, right? But underneath that play button is one of the most massive, most complex computer systems ever built. Today, we're going to pull back the curtain and look at the incredible engineering that powers this streaming giant. And to get started, you have to appreciate the absolutely bonkers scale of it all. So first, let's just talk about the people. YouTube has over 2 billion monthly active users. That's more than a quarter of the entire planet logging in every single month to watch videos. The system has to be ready for all of them.
And what are those 2 billion people doing? Well, they're watching a lot of videos. Every single day, 5 billion videos get watched on the platform. Just try to imagine the sheer volume of data that represents, being requested nonstop from every corner of the globe.
Now this number might be the most staggering of them all. YouTube is responsible for 37% of all mobile internet traffic. Think about that. It's like a constant global fire hose of data that just dwarfs almost everything else out there. So that brings us to the big question, right? How on earth do you build a system that can handle that kind of mind-boggling scale without just collapsing? How does it serve up literally billions of videos instantly to people all at once? Well, that's the system design problem we're going to unpack. To really get it, let's follow the journey of a single video. It all starts the moment a creator hits that upload button. This is ground zero, the first critical step in getting content onto the platform. And this right here is the high-level blueprint for what happens next. It's not one single action. It's more like a beautifully coordinated dance between different servers, massive storage systems, processing queues, and databases. All have to work in perfect sync. So let's break that dance down. Step 1, your video file lands in what's called original storage. Then in step 2, a notification goes out to a fleet of transcoding servers, basically telling them, hey, we've got a new one, get to work. Step 3, once it's processed, the video is sent to a different storage location and shot out across a global network. And finally, step 4, these things called completion handlers update all the video's info, like the title and description, and flip the switch to make it live. Okay, now for what I think is the real magic. That processing step we just mentioned, it's called transcoding, and it's arguably the most important and the most computationally expensive part of this entire system. This is the secret to how you can watch videos seamlessly. So, what even is transcoding? Well, in the simplest terms, it's taking that one high-quality video file you uploaded and creating a whole bunch of different versions of it. It makes copies in different formats, different resolutions like 4K, 1080p, 480p, and different file sizes, all optimized for different situations.
So why does this matter so much to you when you're watching? Well, first, compatibility. It makes sure the video will actually play on your iPhone, your Android, your laptop, whatever. But here's the key. It allows for adaptive quality. You know when you're on spotty Wi-Fi and the video quality dips for a second but keeps playing instead of buffering? That is transcoding in action, seamlessly switching you to a lower quality stream so your video doesn't stop.
So, how does YouTube manage all this processing efficiently? I mean, it's not just transcoding. It's also got to generate thumbnails, process audio, maybe add watermarks. They use a model called a directed acyclic graph, or a DAG. Just think of it like a really smart workflow. Instead of doing everything in a single, slow line, it breaks up all the jobs and runs them at the same time, in parallel. This makes the entire pipeline incredibly fast.
All right, so our video's uploaded, transcoded, and it's sitting on YouTube servers ready to go. Now, let's flip the script. Let's look at what happens on your end the second you hit that little red play button.
Now, here's something you might not know. You aren't actually downloading the video file. Instead, you're streaming it. Your device receives a continuous flow of tiny video chunks, just enough to stay a few seconds ahead of what you're watching. And those chunks aren't coming from one central YouTube server. They're coming from something called a content delivery network, or CDN. Now we get to the real secret sauce. The clever optimizations that make this whole global system not just possible, but also fast, secure for creators, and cheap enough to actually run without going bankrupt. See, to handle billions of users, you can't just buy one giant supercomputer. That's called vertical scaling, and you hit a hard wall really fast. Instead, YouTube uses horizontal scaling. They just keep adding more and more standard servers, thousands of them, to a massive distributed pool. This idea isn't just a technical choice. It's the fundamental principle that allows the entire modern internet to exist. So how do they make it feel so fast? It all comes down to physics. The speed of light is a real limit, so to make data travel faster, you have to shorten the distance. YouTube does this by placing these CDN servers all over the world. So when you watch a video in, say, Tokyo, you're probably streaming it from a server right there in Japan, not one all the way in California. That tiny distance makes playback feel instant.
Of course, with all this content, you have to protect it. YouTube uses a bunch of different layers. They use digital rights management, or DRM systems, and strong AES encryption to stop people from just ripping the videos. And of course, for simple, clear ownership, there's always the classic visual watermark. And finally, how do they afford all this? Because let me tell you, streaming petabytes of data from high-speed CDNs is incredibly expensive. Well, the strategy is genius. Turns out, a very small number of viral videos get most of the views, so YouTube keeps these hot videos on those expensive, super-fast CDNs. The millions of other videos that get watched less often, the long tail, are streamed from YouTube's own, much cheaper servers. It's a brilliant way to balance cost and performance.
So there you have it. From the mind-blowing scale to the intricate dance of transcoding, global CDNs, and clever cost-saving tricks, the system design of YouTube really is an engineering masterpiece. It was built perfectly to solve the challenges of the on-demand video internet we know today. But that leaves us with one final thought. As we move into a future of immersive VR, real-time live streaming, and interactive content, what new, even harder problems will the streaming platforms of tomorrow need to solve?